So we meet again in the classroom. Okay, so I think this is too dark. The next page I will just use the white paper for the class. So my plan for today's class is I think just finishing up the last part. So the way we start the chapter or the engineering of math is by differential equation, in which the differential equation is basically one of the I would like to say fundamental aspect for engineering of math, because in applications the differential equation can be applied in every, I think most of the engineering subject, they will use this differential equation, ranging from either like mechanical, chemical, even for like if you look onto statistics, most of statistics, of course, they will look at the differential equations. Okay? So the topic for your midterm, mostly they will cover the differential equations. So we will cover the first order, the higher order, and then the Laplace transform, in which this is actually another way to look transformations with some special integrals, and we call it Laplace transform. So the first two, the first order and the higher order, we will have some specific methods inside, some how to find the possible answers. Okay. Now, from what we have done before, usually when we deal with calculus, like in calculus 1 or calculus 2, usually we deal with some equations and then you need to find some solutions. Now in differential equations, because we are dealing with the differential as an equation, so the solution should be what the possibility that the equation can be. So for example, you have like dy dx equal blah blah blah. You need to find the equation y equals something, and that y equals something can be many. It can be many. It can be a lot. Okay. Now let me go through the next aspect for this class for today is the solution curve. Okay. Before we are going through the many solutions. So before we go to many solutions, like for example, consider the function y equal 1 over x. Okay. Like if we draw this, more or less, this is, I think, should not be, yeah, okay. So this is y equal 1 over x. Okay, we know this functions that it will not reach 0, right? So we need to have some definition here that this should have some exception that this is not defined at 0. So we need to exclude 0 from the interval, right? And this is just usual 1 over x. Okay. But if we think some differential equation, for example, x y prime plus y equals 0. So if we think this differential equations, this y equal 1 over x, if we try to complete the solutions, and if we try to find the first derivative, what's the first derivative? It's negative 1 over x squared, right? So if we put into our equations, so x, 1 negative x squared, and then plus 1 over x. This is true, right? This is true. So this y over x can be solution. But of course, when we need to write the solution as a curve, we are going to consider the interval. Okay, so need to consider interval. So need to consider let me write some parts that important. So y equal 1 over x is one solution for xy prime plus y equals 0. Okay. So we can say that this can be a solution for this differential equation. Let me write maybe with black on interval not containing 0. Okay, not containing 0. So we need to decide the interval. Okay. So from the function itself, we can choose the interval. We can choose this negative part, only this, or this interval. Okay. So when we draw the solution out of the differential equation, we can have two possibilities for the curve. Okay. The first one, we take only the positive. This is the same 1 over x, but this is on interval from 0 to infinity. So we call this a solution y equal 1 over x. Okay. Okay. So the thing that you need to consider is how you are going to define the solution, okay? Which interval you are going to look at. Okay? So that's also important. Okay? So interval. Okay? So interval for defining the solution curve. Okay? Solution curve. So the graph, let me write. So the graph of solution, because before I'm writing psi for the functions, let me write for functions psi of an ODE, ordinary differential equations, is called the solution curve. And of course, the function should be differentiable, should be continuous for some interval. Okay? For some interval. Okay? For some interval. So let me write here. Interval can be or okay. For this case, for this 1 over x. Okay. So if I'm giving you another functions and it can be defined in the interval, you need to consider the interval. You need to consider the interval. Okay, that's the solution curve. Okay, now after the solution curve, the next part will be the implicit solutions. Okay. So it's actually it's not too far from your calculus actually, but we are going to look at different perspective. Okay. In calculus, usually you find the solutions directly, but in differential equation, the solution itself is finding a functions that are possible to the differential equations. Okay. All right. Now the implicit solution. So relation, let me write relation functions g, let's say g x y equals 0 is an implicit solution of ODE, okay, on some interval provided there exists at least one function psi that satisfies the relation as well. The relation as well as the differential equation on interval. Well, it's a little bit wordy, but we can see from some example. Okay, what does it mean? Maybe not really need the microphone. Okay, remember in calculus, we developed the implicit solution from the equation of circle, if you remember, okay? The equation of circle, for example, we have the x squared plus y squared equal 25, right? And then, of course, now you're already familiar with the implicit. If we do some implicit here, for example, let me just take this d dx at the front. We just need to differentiate x with just respect x, right? So it's just differentiation as usual. But for y, we are going to have 2y and then dy over dx, okay? And then the constant becomes 0, right? And then at the end, we simplify, and then we can write dy over dx is equal to negative x over y. So we could say, because we did the implicit here, we could say that this is differential equations here. Okay, this is the dE. So it's kind of we reverse the process, and we can say that the implicit solution is the first equation. So this is the differential equation. And this is the solution. So we could say that the x squared plus y squared equal 25 is a solution for this dE. Right? So this is solution for dE. Okay. Or to be precise, this is implicit solution. Implicit solution. Okay, implicit solution for the dE. And then the interval, we can define the interval because we know and we can visualize that this is a circle. We can define the interval from the radius itself. Okay, so we can define that, or let me write in more complete here. So we can write x squared plus y squared equal 25 is an implicit solution for dE, that is dy over dx equal negative x over y. Okay, on the interval defined by negative 5 less than x less than 5 And remember, let me check if I have okay, I have. So remember, when we deal with the implicit in your calculus, I think the first calculus, the calculus 1, let me make it a little bit bigger. Okay, bigger. When we have this x squared plus y squared equal 25, okay, our choices, if you would like to differentiate, before we learn implicit, one way to differentiate is we are going to either equaling x squared in terms of x squared or y squared, right? So we can see this can be done by through here or through here. Or let's say through the most usual, maybe this one. So we could have the y is plus minus square root of 25 minus x squared. Okay? And by doing this, you can actually use the same differentiation technique as usual with the square root, and then you have plus minus. And if you imagine the visuals, okay, if we reverse that the question is asking what is the solution for this DE, we can imagine that we can make through directly implicit like this, the whole circle, because we do the implicit differentiation, or we could have the positive and negative part from the plus minus square root 25 minus x squared, okay, from here, from this one. So we call this implicit, explicit, axis. Okay, this is to show you how we can go from here. Okay, so every time you see anything that has two variables, we can look on the implicit solution. Okay? So here's the positive one. Okay? Having the interval negative 5 to 5 is the same interval, all is the same interval. Okay. Now that's implicit solutions. Okay, implicit solutions. We haven't yet really comes up with some like specific techniques or method. Okay, this is just introductory. Okay? Maybe next week we will go for that part. Okay? Now from this implicit and from the solution curve that we have defined before. Now, if you have differential equations, then probably the solutions can be done by many solutions, or we could say families of solution. So when we solve the nth order DE, let's say the f and then x, y, y prime, y double prime, dot dot dot, y with power of n. Like it's in order n. We seek the solutions. We seek because it's n order, we need to seek an n parameter family solution, family of solutions. Let's say the solution is in function g to differentiate with f. So this is x, y, and then it's become a constant 2, dot dot dot, constant n equals 0. This means, okay, let me write. This means single DE can have infinite number of solutions. Okay. Now, because we have infinite number of solutions, we need to restrict which solutions that are important. Okay, which solutions that are important. Okay. They are important and then meaningful for us. Okay, first, a solution that is free from or free of arbitrary parameters is called particular solution. If we have DE, for example, DE is xy prime minus y equal x squared sine x. Now we can verify that y equals cx minus x cos x is explicit solution. Of the E. Okay, this is example, just to illustrate. Okay. And then, okay, if we change the constant for trying some number for the constant, we can see some interesting figure that are coming out from this solution of differential equations that can be a solution. So we see that this C is changing, and you see that it has some certain specific behavior. Okay, this behavior. So this is also I think important to see that they have certain property. Later on, we will introduce you to the slope field. It's also finding the solution curve through some we say through some slope that is possible for that differential equations. Okay, and then we can plot with some graph. Okay. And then I think the last section, or maybe the last part for this introductory, is we can have the solution in piecewise defined equations. Okay, piecewise defined solution we call. So if we have dE x y prime minus 4y equals 0, okay. Now we can verify y equals cx with power of 4. Okay. Because I think it's quite possible from the structure x, y prime for y. So it has x, and this is derivative. So which means that if we want to make this the same, the order the same, so the possible thing is with something x with power of 4, right? Okay. You see that this x derivative becomes 3, so x3 is 4, and minus with some 4, so it should be at 0. So, and depends on the constant, we can see some variation in the solution. Okay. So from here, if we develop the curve, okay, let me check whether I draw the curve. Oh, I have drawn the curve here. So we have some solutions that can be that can solve the differential equation. So when we have c negative or positive, it can be some solutions. Okay, when c is equal 1, and we can have the interval as well, the positive interval and then the negative interval here. And because we have these two c, okay, 1 and negative 1, we can see that we can develop the solutions that is in piecewise function. So first is negative x with power of 4, and the second is x power of 4, and we can see the development with the interval itself. So this is x less 0, this is x greater or equal 0. Okay. So we can have the piece, this is the piece defined, piecewise defined, sorry. So how do we know we are going to look for piecewise or not? Well, it depends on the restrictions that the equation had, or maybe the questions, the questions that asking. Either it's asking directly the piecewise part, or just asking like how many solutions there are possible. Then this is one of them. Okay, one of them. Okay, one of them. And then another thing, we also have. It's called the singular solution. This is like an extra. Okay, this is like an extra. This is, we call another name. This is the extra solution. So this solution can't be obtained by specializing or let's just say specializing any parameter in family of solutions. So what does it mean? So this mean is it's the solution that outside of the equation that we have. Okay. For example, the easiest way that it will be the singular solution. Usually, it will have the structure or the equations. Usually, y equals 0. Okay, y equals 0. So it's not a member of the family of solutions, but it might be the solutions. Okay? Y equals 0. So we call that this is like extra solutions that might be. Okay? Or we call this as a singular solutions. or we can write maybe outside of family. Okay. Let me sum up, make some short summary and make some notes for you. So if we define this system of differential equation, so the system is, the system is two or more equations involving the derivatives of two or more unknown functions of single independent variable. Or this is for ordinary, okay, for ODE. Okay. So system of differential equation for the ordinary one is two or more equation involving the derivative of two or more unknown function of single independent variable. So what does that mean? It means that, like I think on Tuesday class I mentioned that you may have more than one dependent variable. For example, dependent variable can be y and x, and then the independent maybe just one is t. So we call that the ordinary differential equations. Okay, if the independent is more than one, we call the partial. Okay, the partial system in differentials. So for example, let's say the example here. So if I write dx over dt is f, and then t, and then x, y, which means that the t is our independent. So this is the independent one, and these two are our dependent. Okay, and maybe we have another one like dy over dt. Let's say this is g t x y. Okay, same. This is the independent. This is the dependent. So this means that the x and y are dependent and t is independent. Now from the system, we are going to find our solution. So solution of such system from this example, this can be defined as a function of t and y function of t defined on interval I that satisfy the equations. Okay, so this is what we are going to look for. Okay. that's the first part, okay, of introductions. We have the second part, okay, of introductions. Well, the early classes is just for familiarity with the terms, okay, with the subject. The techniques that I think in the first half of the semester will be all the techniques you have learned in calculus. Okay, the second part is called the initial value problem. I will just write the important one, okay, and then maybe skip some parts that I think not really important. So if we have some n order, let's say dy over dx, the differentials with the order n, then we can write the general forms x, y, y prime, as usual, until y, let's say n minus 1. This is from the, I think, the Tuesday class, right? And then if we know, okay, if we know some initial condition that can solve this differential equation, then we might have solutions directly. Okay, we can have solutions. So, and it depends on how high the order will be. Okay, so let me just write first all the initial conditions. This is initial condition for the first one, and then when you have the first derivative, and then when you have some n minus 1, okay, which means if you have, okay, let's say dy over dx equal some fxy. To solve this, we are going to need just only one initial condition, which is just we need y x0 equal y0. Okay. Maybe let me write a little bit here. So to solve, we need this. Okay. This is initial condition. And how many initial conditions we need, that depends on the n. Okay, that depends on the n. So when we have higher n, maybe 2, the second order, so x, y, y prime. We need at least 2. So first is this, and the second, and y prime. Okay. How to imagine that this is logically makes sense? First, you can imagine the differentials, and probably you can imagine through integral. Okay. When you integrate, you have a constant, right, that you need to look for. So the more order you have, okay, the constant can be more than 1. Okay, so that's how you can see this differentials also works similar, not really the same, but it works similar. And you will know from, I think, from some practice. Okay, from some practice. So the whole thing here, we call the initial value problem. So initial value problem is a problem, a set of problems that you need to solve some differential equations, and you need to find the solutions. But because we have initial conditions, we are going to have restricted solutions that is exactly that answer. So like if we have dy over dx, like the first order, Of course, we only need one initial condition, and that's when you calculate, compute, and you get the number. So that is the answer. Okay? That's the answer. And when you increase the order, then the initial condition also need to be increasing. So we need maybe if order 2, we need 2 conditions. If three conditions. Okay. And you will see from, I think in the exercise they will give you directly, like if this the first order, and you will be given like one initial conditions. Okay. Okay, that's the initial value problem, and I think not really need for example. We're going to look later on. Okay. Okay, after this initial value problem, I think okay. Let me continue for a little bit more. The next part is called the existence and uniqueness. So this is actually, if you are given the differential equations, the first thing, how many solutions we have, or before how many solutions, does the solution exist or not? And maybe that will be really important and really fundamental for you to know beforehand. So maybe if there's a solution of the problem exists. If exists, is it unique? Now we need to develop what does it mean? Okay. Okay. For the ODE, the first order ODE, we need to ask, does DE possess solutions? Do the solution curves passing point, certain point x0, y0? And then other questions, when can we be certain there is precisely one solution curve passing through x0, y0? Okay. Okay, now we need to develop some assumptions to answer this question. Okay. So this question is actually asking first, of course, the possibility of the solutions. Passing a point means, remember that before we have initial value problem. That is the point actually. That is, we are going to see that the point that in the initial value problem, there will be in our solution curve. Okay? Now we need to develop something here. Let me just write with my own words here. Existence related to existence. So if a function is continuous around, let's say, the point AB, okay, or maybe before this, maybe write some assumption here for dE dy dx. It's actually the same thing here, just to make sure that we are on the same page. And then initial value y a is equal b, of course at AB, right? So that's the our initial value. So if the function is continuous around this AB, our initial value, and this is an open interval around x equal a, then let me just finish the existence and then we can finish this class. Then at least one solution exists on an open interval, same thing here, around x equal a. And if fxy is not continuous, a solution is not guaranteed. So not sure whether there will be a solution or not at that point. And then we ask, x equal a cannot be the endpoint. The endpoint of the interval. Of course, we can imagine like a curve like that. So, of course, the existence will be built around continuity. Okay, will be built around continuity. So with that continuity, there will be guaranteed existence. But if we maybe something here, some discontinuity, then we cannot sure that there will be a solution. Okay. I will stop it here. Okay. And I will continue the uniqueness, and then after that maybe we are going to going through the first